I was out in the field last week preparing, out there with a field spectrometer, something you wear on your backpack, to try to collect some measurements that we can use to compare emit with. So yeah, I can't emphasize enough how excited the science community is for this and the remote sensing community is to get these spectral measurements in a detail that we haven't had yet before.
Hello, everyone, and welcome to another episode of Eyes on Earth. We're a podcast that focuses on our ever-changing planet and on the people here at AROS and across the globe who use remote sensing to monitor and study the health of Earth. I'm your host for this episode, John Holt. As regular listeners know, AROS is the home for NASA's Land Processes Distributed Active Archives Center, or LPDAC, which is an enormous trove of Earth's surface data collected by satellites and by sensors on board the International Space Station, or ISS. Today, we are talking about an exciting new mission whose data will be shared through the LPDAC. It's called the Earth's Surface Mineral Dust Source Investigation, or EMIT, and it's seeking to help us understand something we don't know nearly enough about. That is, dust. Clouds of dust kicked up in places like the Sahara can travel thousands of miles across the planet. We can see those clouds in satellite imagery, but we don't typically know much about the composition of that dust. That is a huge blind spot, because those unknown characteristics, such as the particle's lightness or darkness, have an impact on what they do. The warming and cooling of the atmosphere, snowmelt, ocean and rainforest fertilization, and even cloud formation can all be affected by dust cloud composition. So EMIT will gather data on dust sources from its perch on the underside of the ISS. That data will help scientists to map and understand the composition of the minerals on the Earth's surface. Here with us to talk about EMIT are a few members of the EMIT science team. David Thompson, who works at NASA's Jet Propulsion Laboratory, is the instrument scientist for the EMIT mission and an expert in the novel spectroscopy methods that it will use. Phil Broderick works with Thompson at JPL as a research technologist. We're also joined by Raymond Koecheli of the USGS, who uses spectroscopy data for vegetation and mineral characterization. David, Phil, and Raymond, welcome to Eyes on Earth.
Thanks very much, John. It's great to be here.
Good to be here, John.
Thanks for having us.
Let's get started with the big question. Why are we so interested in learning about dust sources? I mentioned a few things in the introduction, but let's expand on that a little bit. What does atmospheric dust do to our planet? What are we trying to figure out here?
I think one of the main problems at the core of the EMIT mission is that we really don't know a lot about dust's role in the Earth climate system. We know that it can have a significant impact. We know that there are dust storms and that there are dust particles throughout the atmosphere that can be carried thousands of kilometers on winds, and that they do have an effect on incoming solar radiation. So we know that dust is doing something, but the models that we have that predict the dust's role in the climate system have a lot of unknowns. And in particular, they don't know a lot about the composition of dust. And this is a critical factor that can determine whether dust is a net warming effect on our climate or a net cooling effect. So as we think about how Earth's climate is changing and will change in the future, dust is going to play an important role, but we really don't know whether it will be a net warming or net cooling influence. And that's part of what EMIT is designed to answer.
Anybody else want to jump in there?
Yeah, John. In my own research, I've examined dust collected both from source regions in the western U.S. and dust from snow collected across Colorado at the end of the winter season. And as you stated at the beginning, we find these samples to vary in their light absorbing properties, both in the visible region of light that our eyes can sense, and then the longer wavelengths of light from the sun, that's the near infrared and the shortwave infrared. And in other studies by scientists, they've looked at these strongly absorbing materials and found that when they're in snowpack, they can accelerate snowmelt and change runoff to streams, and thereby affect the timing and availability of water resources. And certainly, as we know, in times of drought now, those resources become more precious to us. And so while my samples and samples from other local scale studies tell us there's this variability in the light absorbing properties of dust, we really lack that global survey of dust composition.
What do we know about Earth's surface minerals now, and what data gaps will EMIT fill? It sounds like there is information, but maybe it's just not globally available, or is there global information, but it doesn't match up? How big is the gap, and what do we know at this point?
We've been waiting for orbiting sensors like EMIT for decades so that we can discriminate a wide range of minerals from one another and map their distributions on the Earth's surface. So over the past 40 years, we've had sensors like the Landsat series that can be used to differentiate a few of the iron-bearing minerals like hematite, which is iron oxide, for example, like the rust that forms on iron-bearing metals like steel, or goethite, which is an iron hydroxide. And then we've also had the Aster sensor, which has more spectral sampling in that shortwave infrared region of wavelengths that allow us to map some broad classes of clays and carbonates. But EMIT will be the first Earth-pointed sensor in space that will allow us to describe and characterize a great number of minerals in very fine detail. We're going to see a big change in what we can tell about the Earth's surface from EMIT than what we could tell about the Earth's surface from previous sensors.
This is the first time we're going to be measuring this from space with this level of detail.
Yeah, I would say we're looking at an order of magnitude or 2 orders of magnitude of additional mineral information that we'll be able to derive about the surface by using EMIT.
I'll just give a little bit of context here as well. So the current Earth system models that attempt to utilize information about mineralogy use interpolations of data that have been collected around the globe at point sources on the ground. And you can think of it as tens of thousands of data points, right? But globally, that's incredibly, incredibly sparse. And these are effectively spatially interpolated throughout the entire Earth. This gets us entirely outside of that framework and lets us actually retrieve every pixel.
So to do kind of a comparison here, when we're talking about land cover maps made with Landsat, which we do a lot on this show, we use the Landsat data and then we have the on the ground, the sort of in situ data, and we put those two things together to make sure we have the best map. And at this point, we only have the on the ground sample points.
Yeah, I think that's accurate. So as before, where we were digging up individual soil samples, maybe a few thousand worldwide, and trying to figure out globally what the mineralogy of these regions are. And now we'll just be able to take a picture of the minerals from space.
Other types of remote sensing have just basically treated a rock as a rock. All the rocks are the same. But when you can see the defined spectral details, you start to see the chemical variations, and the world of rocks kind of really opens up to you, and you start to understand what geologists see when they look through that hand lens at a rock. They're looking at all these little reflections and refractions of light through crystals, and they can describe in great detail what the rock is comprised of and tell you about the geologic history. Now we're going to be able to do that with spectroscopy because we're going to be able to see those little bumps and wiggles in the spectrum that's measured by EMIT.
So let's talk about the technology here a little bit. EMIT uses spectroscopy, which we've started talking about a little bit here, and it's going to gather information across hundreds of bands of the electromagnetic spectrum to help us to understand what makes it so valuable.
The technology is quite simple. It's just like a camera where you take an image of a scene from space, except for every pixel in that camera, you have a whole spectrum. So our eyes see in 3 channels, red, green, and blue, and an instrument like Landsat might see in a handful of channels. EMIT will see the full spectrum of radiation from the ultraviolet out through the shortwave infrared in hundreds of contiguous channels. And so it's a very different kind of analysis that you can do when you have that information available, because you start seeing patterns in these spectra, shapes that is, in the way that different substances on Earth absorb and reflect radiation. And it's those shapes, those subtle signatures that are distinct to all these different materials on the Earth's surface that allow EMIT to classify objects remotely, to know what the surface is made of from afar. And that's what gives us the power to map minerals.
One of the amazing things about spectroscopy is how truly intuitive it is when you start to look at a full waveform, and you can use that to pull apart the composition and the constituents of the surface and to try to figure out what is really there. I had the pleasure of going and talking with a second grade class this week where we explained the EMIT mission, and we put up some different spectra of different types of minerals. And then we had a little portable spectrometer that we pointed at different materials, and second graders had no problem pulling out the different components and identifying and matching what was what. Now, obviously, I'm talking about a much simpler example, right? And there are incredible complexities in this problem. But at a broad level, there's a lot of just general intuition that you can get immediately from looking at each and every individual spectrum.
One of the things that really got me interested in spectroscopy when I first started at the USGS was I would see these spectral plots produced by a spectrometer. And, it was kind of mysterious. You have the, energy coming from the surface as a function of the wavelength, right? And then you'd see these little bumps and wiggles. And I would take that to the person who brought me into the survey, hired me in, and he would just be able to look at it and say, oh yeah, that's kaolinite clay. That's a little bit of algae that's on the surface of the clay. And it's got, a lot of water because you can see this dip here. And so I think that intuitiveness that Phil talks about with the class that he interacted with, it's such a powerful thing that you can attach meaning to the pattern, but then you can also put that into a computer system and then try to find those patterns of materials across the surface of the Earth or other planets.
That's so fascinating. So the person who brought you into the survey could look at one of those scatter plots and go, that's some algae.
Oh, yes. And he is involved with the EMIT team. He's Roger Clark. He's now an emeritus with the USGS. But yeah, he just has this incredible knowledge of spectral shapes and positions of the absorptions and just can rattle off, in a few seconds what the composition of the material is by looking at the spectrum.
Now, does that mean that all of you can do that as well? Like, do you have quiz nights or something? You try to stump one another with this or what?
Well, we should, because some of my colleagues, Todd Hafen and a few others, we have joked about Spectral Olympics, where we kind of do that thing where it's like challenges to measure the best spectrum, or to, a wall with different minerals on it. And then you got to scan the wall and, have the best identification, prediction ability and things like that. So, yeah, we talk about that kind of thing all the time.
Yeah, and after you get really good at it, after you've done it for many years, it almost becomes like a superpower where you can take a scene acquired remotely from the air from orbit and see like the age of the road, how long it's been since it's paved. You can look at green grass and know whether it's astroturf. So people get really good at this.
Let's talk about the kinds of questions that you expect researchers to use this EMIT data for. Do any of you have specific questions that you're going to investigate yourselves? I mean, are you going to be aging the roads, for example, if that's possible? I'm expecting maybe that's not the first thing on your plate, but what kinds of things can we be looking at with this? And how broad is this? Is it just dust, or is there valuable information beyond the sort of marquee questions that we read about when we read about this mission?
So in addition to looking at the surface, these spectrometers can also see absorption by gases in the atmosphere. So we're sensitive to a wide range of atmospheric constituents, including greenhouse gases like CO2 and methane. And imaging spectroscopy has been used in the past to find individual emitters of, say, methane, fugitive emissions from, say, oil and gas infrastructure or dairy farms. And these have been used to catalog emissions on regional scales. But EMIT now joins a fleet of orbital imaging spectrometers that's going to be making these measurements from orbit over really wide areas. So it will be interesting to me to see what methane emissions, for example, we spot in all of the oil and gas infrastructure that we fly over. And this is a great possibility for mitigation, really, because a lot of these super emitters put out a significant fraction of the world's methane. And if we can find them and remediate these leaks where they occur, it's a win for everybody, including the oil and gas companies that are losing revenue now, if they have a leaky tank.
So now we might be able to see a flare, or we might be able to see some heat, but you're talking about having a better sense of this is methane. It's not just an image, or we see heat or something. You're talking about actually pinpointing the gases themselves.
We can actually detect the enhancement of methane due to a localized leak at some facility, if it's large enough, of course, and image that methane plume by analyzing its spectrum.
Raymond, what's the first thing on your plate when you get your hands on this data?
The work I have ongoing right now is to map surface occurrences of elements that are critical minerals to the U.S. economy and to national interests. So these are elements that are needed for green energy technologies, things like lithium for batteries, and rare earth elements like dysprosium, neodymium, samarium that are used in powerful magnets and generating electricity. So this active research includes both looking for new sources of these minerals and these elements, but also investigating previously mined areas and the remnant rock piles in those previously mined lands, which may also be a source for critical minerals.
Wow. Okay, so I just want to say this out loud so that I understand it, and correct me if I'm wrong here, but I think what I heard you say, Raymond, was that you've spent more than 2 decades studying Earth's surface minerals, important minerals to all of us in the U.S., especially now as so many of us transition over to electric vehicles, if that's the world we're going into. And you've done all of that without the ability to characterize these minerals from space so far.
Yes, you've got that right. I've been lucky in my career to work not only on these geologic problems and questions, but also on questions about vegetation, species composition in forests. For example, forests of Yellowstone, where if you have certain trees in certain areas, then you can get a more accurate count of the grizzly bears because you know those grizzly bears are going to be there at a certain time of year to utilize that resource. And then studies of the transformations of the landscape by fire. As fire comes through, you can change the composition of the minerals in the surface and you can affect plant regrowth. And of course, humans do a lot of activities following fire to try to encourage certain regrowth to occur so that you stabilize the surface and avoid catastrophic runoff or debris flows. So I've been able to use imaging spectroscopy on a very localized sense for that, but not been able to use it on a wide-scale basis across the Earth. So we're really at a great point now in Earth remote sensing. We're going to begin to have data from EMIT and from other sensors that are being launched by other national space agencies. And so we're going to be able to do these kinds of studies on a much larger basis.
Let's talk about timelines now. What are the timelines for availability? How are users going to find this information? Are we going to be seeing tutorials in the future to help guide people through the use of this data? I know it's not like the day after the sensor goes up, we start getting data. There's a lot that goes on in the interim.
EMIT has a fairly ambitious and aggressive timeline. After launch, we'll be installed onto the space station by a robotic arm and then have about a month of on-orbit checkout where we'll be checking out the systems to make sure that everything's functional. We'll be talking to the computer, making sure that the spectrometer is still well calibrated and just making sure that the system is ready to take science-grade data. And at that point, our data collection begins. And maybe a couple of months after that, start releasing data products out to the DAC. At that point, it will be available to everybody. The first things to come will be what we call the radiance measurements, which are just measurements of illumination at the sensor. Subsequently, there will be releases of surface reflectance. That is the ratio of outgoing to incoming illumination at the surface. And this is where all the interesting mineral signatures live. But to do that, we've had to strip out all of the intervening influence of the atmosphere. So it takes a little bit longer. The reflectance will come out, and then after that, maps of minerals. And so all of these products will be delivered to the DAC for everybody to use. All of EMIT's data is going to be public. And then there's a final reprocessing that will occur about a year after launch, probably, that will give us a chance to revise our methodology. If we come up with updates to our data processing, we'll be able to implement it at that time, and people will get a revised version of the data.
So that is pretty aggressive, just a month of checkout, and then you'll be collecting data. But I want to put a finer point on one thing in particular. Did you say maps of minerals will be among the data sets that you'll be able to download from the DAC?
Yeah, that's right. EMIT is going to be distributing mineral maps in addition to all of the other products that we produce. So if somebody has data from their backyard and want to figure out what EMIT found, in their locality, they can go to the DAC and download that and learn whether there's calcite or kaolinite out there.
We've been talking to David Thompson, Phil Broderick, and Raymond Kokoli about EMIT, a mission whose data will soon be available through the LPDAC. Thank you all for a fascinating conversation.
Thank you. No, it's fun.
Thank you. Yeah.
And thank you to the listeners as well. Be sure to join us next time to learn more about satellites, remote sensing, land change, and so much more. You can find all our shows on our website. That's usgs.gov/EROS, which is usgs.gov/EROS. You can also subscribe on Apple Podcasts or Google Podcasts and get the latest episodes delivered to you.
This podcast
is a product of the U.S. Geological Survey, Department of Interior.